Hi, this is video 820 from the book Mechanics of Material, Hibbeler's the SI edition, and this is about problems on combined loads. Problem says like that the plate has a thickness of 20 millimeters, and the force P equal to 3 kilonewtons acts along the center line of this thickness, such that D equals to 150 millimeters. So what is this? We have the plate, and we know that this is the height of the plate, which is 200 millimeters, but then if I look at it from the center, kind of pointing at the screen, it's going to be, how much is it? 20 millimeters, so the thickness of that. And that the force is not acting along the center line of the beam, but above it, at a distance that is given there, but we don't know the distance between the center line and the force, so we need to calculate that at some point. It says, plot the distribution of normal stress acting along the section AA, which is this one here. Just normal. They don't talk about any shear force or shear stress or anything, and we're going to see why. Basically, there is nothing to do there. I have extracted some data from the problem. It says that this is the normal load applied to the beam, P. I have the thickness, and I have the distance from the base, and I should add here also the plate height, like this. I'm going to call it H, and that's going to be those 200 millimeters. There we have. I have on the other side, on the right side, I have the drawing, so I can make some annotations and everything. And this is a very straightforward problem in the sense that the only thing we need to do as a beginning is to make a cut in that section AA to see what are the reactions appearing from that, by separating those two parts. And we're going to work with the left part of it. I'm going then to draw this, let's do it in blue. So let's imagine that I'm kind of cutting that like this. This is kind of matching the upper figure there, sort of. Yeah? So I have this part here, and I have, let's call it that this extends to section AA, which corresponds to that one on the top. We'll put some dashed lines here, like this. And as they're talking about the distribution of normal stresses acting along this section AA, I kind of need to know where are all these stresses going from top to bottom. So I'm going to put one, here it is, one name to this point. I'm going to call it A, no, but with this one. Or actually, let's call this B, and let's call this one A. Then I'm going to draw the center line of the whole plate. This is the center line. I'm not going to call it neutral axis or anything. That's the center line there. Also, I'm going to draw, again, the force, kind of replicating the figure on the top. And this is P. I have a distance applied to it and everything. But what I'm interested on is in drawing what are going to be the reactions when I make the cut. And because of the way this is working, kind of, I only have a normal force applied to the plate. What I'm going to have only here is going to be a normal force reacting to that normal P. I'm going to call it N. And I'm going to have a moment. So this force P is going to try to, remember, when we make a cut and we want to find out what are the reactions appearing in that cut, and if we're going to take moments, that moment is going to be taken around this point. Yeah. So the moment that force P is going to create around that point that I'm marking right there is going to be in this direction. Hence, I would think, I could be wrong, but the calculations are going to tell me in the end if I was wrong or not, that the reaction moment in the cut is going to be like this. So I'm going to draw it in that direction. So to use another color here, it's going to be this one. So I'm going to have only normal force and bending moment as a reaction, or moment as a reaction there. So what means that if I want to combine them and form my equations of normal stress, because that's the only thing they're asking me to find, then I'm going to have the normal stresses in that section AA. It's going to have a certain shape. First, we're going to have the normal stress due to the normal force. So it's going to be the normal reaction force divided by the area. And then we're going to have plus minus here, the moment times, I'm going to call it C divided by I, where I is the second moment of area, and C is the distance from, just talking about bending moment, from the neutral axis, that if I forget the force, just to focus on the bending moment. So this is going to have, the neutral axis is going to coincide with the center line of that plate, just for the bending moment, not for the combination of both. So it means that I'm going to have one value of stress here and one value stress here, and it's going to be a nice distribution going from top to bottom or bottom to top. So they're going to be contrary, that's why I put them plus minus here. But then when I combine them, everything is going to present a different shape. Now I have that, so what means that the next thing I need to do is to find what are the values of those reaction forces in the cut. And we're going to call them internal load calculation. So let's put here, from here, internal loads calculation. Beautiful. And I know that I'm going to have only, if I do it properly and I say, you know what, I'm going to use a reference system such that the axes are like this. So I'm going to have my x-axis here, my y-axis here. So which means that on the z-axis is well pointing perpendicular to the screen. So it means that the only forces or equilibrium conditions I need to apply are going to be in the horizontal axis and then in the rotation, kind of in the z-axis here. So to that end, I'm going to bring a solver here and then going to say, write my equations as static equations, so it is not evaluated. So moment around which point? Well, let's call it O, and I'm going to say which point is O. I'm going to have this, I'm going to put it a little bit kind of bolded. I'm going to call point O this one here. This is point O. There it is. Everything is happening in that point. So if I have that, I need to calculate what is the distance between the line of action of the force and the center line of the figure. So which means I need to know what is this distance here. And I'm going to call it, I used already D, so I'm going to call it R. So that R, I know that the distance from this point to this point here, this one here is, how much was it? And let me put it a little bit like this, and then I'm going to get rid of, or not get rid of, but move my reference system here. There it is. So this is going to be, how much was it that the 150 millimeters. There it is. So that's 150 millimeters. So if I subtract 150 millimeters minus the half of the distance of the height of the plate, then I'm going to end up with the value R, that's the one that I need to have for the calculations here. So I could actually calculate that R beforehand, distance from the line of action of force P and the center line of the figure. If there is a kind of spelling mistake in center line, apologize for that. It's giving me some red underline there. So that R, we said, it was going to be then D, 150 millimeters, minus half of the height of the plate, like this, 50 millimeters. There we have it. Then I can jump to the calculation of moment, as equilibrium, and that's going to be that the force P is going to create a positive moment. The reaction moment is going to be negative. So I can say that P times that distance R that I got before, P times R minus the moment reaction is going to be equal to 0. And I get already the reaction moment there. Now, the other axis that I said that is what's going to be only, or we're going to have only kind of forces, reaction forces, is going to be in the horizontal axis. Then in that case, I'm going to copy this just to repurpose this formula here. And here I say that N, which is the reaction force, minus P, which is the only horizontal force I have, is going to be equal to 0. And I have there that one. Perfect. Just want to change this one to a better unit. It's not as strong, but I just want to, let's call it to Newton's meter. Yeah. A little bit good, better looking. So now I have the two forces, reaction forces appearing on the cut here and here. So now I need to put it into this formula, then get the values I need. But to use this formula, I need to calculate the section properties, such as the area and the second moment of inertia. So let's do that. I'm going to call it here, maybe here, yeah, section properties. And the area is going to be base, thickness times the height, and then that's going to be thickness times height, and we get this. Change the formatting of this like this. And then we add the second moment of area, moment of inertia, 1 divided by 12 times the base, and the base is the thickness of it, times the height to the power of 3. There it is. Okay, beautiful. Now that we have that, let's jump to calculate the normal stresses. Normal stress calculation. I'm going to divide this formula into two parts because I cannot do it at once here. So I'm going to have one formula for the positive sign, kind of adding the stresses, and I'm going to have another formula for subtracting the stresses. But we need to understand what goes with what does it mean. So if I kind of take this part from here and then I just steal it, and let me try to do it a little bit larger. Here. This here is going to be my point B, and here is going to be my point A. So now, because of the normal force, we're going to have a normal stress that corresponds to this part here. So how that normal stress distribution looks in the figure, that's going to be, let me just move this one like this. Let's put it in the back here. I'm going to have this shape like this. Oh, this is ugly, this one. Let me try to do it in one go. Better. So this is going to be the distribution of normal stresses due to my normal force, N, something like this. And it's in traction, and we can agree on that. And this is the part that says, well, this is N divided by A, like this. Now, what's going to happen with the bending moment, or the stresses, distribution of normal stresses produced or developed or created by the bending moment? So what's going to happen here is that, as mentioned, kind of that I assume that this was going to be the direction of my bending moment. But when analyzing everything, I noticed that the bending moment around this point of this force is going to be like this. And this one needs to be then in the other way around, which is negative. That's why I kind of put it here in this area here, negative. So in reality, what's going to happen is that this bending moment is going to go something like this. Yeah? That's the real direction. Remember that I assumed at the beginning, and then if I was wrong, the mathematics was going to tell me that I was wrong, and then it just happened like that. So it means that if I want to draw that distribution of stresses in the upper part, meaning going from the center line of the figure to the top, I'm going to have tension stresses, tensile stresses, and then from the center line to the bottom, I'm going to have compression stresses or compressive stresses. So I'm going to, just to make it a little bit similar to the top, I'm going to have this center line here, and I want to extend it because I'm going to have tensile stresses going in this direction here. I'm going to have compressive stresses going in this direction here. And they are going to, this line of distribution of stresses is going to meet like this in the center. Something like this. So this is tensile, and this is compressive. So important here is to analyze and understand what are the directions of your forces and moments after you have done the calculations, because you're going to assume whatever you want at the beginning, but it doesn't mean that you were right. So you need to confirm or validate that with the mathematics there. So you see that the upper part, when I was talking about this C here, the upper part is going to be, it's going to add up the normal stress created by the normal force and the normal stress created by the bending moment. So I'm going to use the plus in the upper part. In the lower part, it's going to subtract both terms. So that's what we need to do at the moment. So I'm going to have two terms. I'm going to define first for the upper part here, stresses. And I'm going to change this to stress distribution from the center line to the top of the plate. So for that, my C1 that I'm going to call that value is going to be half of what? So it's going to be C, well, in both cases, it's going to be the same actually. So I don't need to differentiate them. So it's going to be half of the height, 100. The only thing that I need to change is the sign in the formula. So I'm going to call this sigma top Just giving it a name. The sigma top is going to be n divided by a plus then m times that c divided by I. I'm going to have 0 kilonewtons. Let me put it in megapascals. No, megapascals. There it is. Then stress at the bottom, those are the limit stresses at the top and at the bottom. And let me just for the sake of everything here, A, to have sigma bottom here is going to be equal again to the normal divided by the area, then minus the moment times C divided by the moment of inertia. There it is. Again, let's put it in megapascals. There we go. So, which means that if I try to make that figure here, or try to draw stresses there, so I'm going to have that, how to call it? Let me see the better way to do it. So I believe I need to maybe copy this. Like that, and then I can draw things. So at the top, I'm going to have 1.875. So which means I could draw something like this, this much. Let's make it big, large here. So this is 1.875 megapascals. Then at the bottom, I'm going to have as compression this much, 0.375. So I can do it something like this. I'm going to put it negative, so I'm going to omit the sign here. So it's going to be 75 megapascals. And because of the way normal stresses because of normal forces and bending stresses due to bending moment are kind of configured, then the distribution is going to go from this point to this point here, something like this, where all this section is going to be in compression, in tensions, right? And this one also is in tension, and all of this is going to be in compression. Now, you see that the centerline of the plate is no longer for bending purposes, or the distribution of stresses is better, the better word, is not the neutral axis. So the neutral axis have shifted from this point here to this point here. And one thing to do would be to, let's see if I can just change the color, put it this way. And the thing is that we need to calculate, so where is that distance, yeah? So one way to do it would be to say, okay, you know what, from this point, from this point to this point, I'm going to call it Y. And let me change this because it changed the configuration of the, I'm going to call it Y, which means that this part here is going to be the whole height of the plate minus that Y. That is H minus Y. So I could use similar triangles to calculate this, meaning that this divided by this, let me just use the laser, this divided by this equals to this divided by this, or the other way around, for example, it could be. So let's do it. Location of the neutral axis. Then we said that we could call it that, let's use a solver, that Y divided by sigma top, this Y divided by sigma top equals to H minus Y divided by sigma bottom. There it is. 2. How much is giving me? Okay, so it's giving me this, but one thing that I need to get rid of because of the similar triangles, I need to work with positive magnitude, so I need just to add this friend here. There it is. It kind of goes, what? No, yeah, 250, what was it, millimeter or something? So doesn't make sense. So that's the position of the neutral axis, meaning that this distance here is going to be there. 0. If we put this as meters, so it's going to be 0.167 meters. Or we can leave it as millimeters as we're talking. 166.6 millimeters. How does it look? Yeah, looks good. And there you go. This is the answer to the question. So what we did was just to summarize, we understood how the thing was, what was going on there by making the cut, drawing the reactions appearing in the cut because of how, for example, the normal force is positioned and everything. I assumed certain values, for example, for the moment there. Then I wrote down my equation saying, okay, if I want to calculate normal stresses, this is the way I should do it, which is represented here. Then what I did was, well, I jumped to make what are the internal load calculations by just, applying the equilibrium conditions just for normal direction to the face, and then for the moment, because there is no shear force here appearing, so that's 0. I got the values of the reaction forces there, moment and normal force, and then I noticed that I need to have the section properties like the area and the second moment of area or moment of inertia there, calculated that. Then I did a small analysis saying, okay, the normal stresses due to normal force are going to be this one, but the normal stresses due to the bending moment are going to be like this. So meaning that at the top, I'm going to add up things, and then the bottom, I'm going to subtract things. That's why the resultant shape of the distribution is this one, like I have it here. So then I have the calculation of all the stresses. And finally, to close the problem, what I did was, okay, now I know that the neutral axis is not coincident with the center line of the plate. So where is the neutral axis? So for us engineers, it's very important to know where is the neutral axis. So using similar triangles, I managed to find where the neutral axis of this case was. And I'm going to call it like this. This is the neutral axis, NA. And that is it. I'm going to put it like this again. Nice problem, very simple, but it's full of concepts that's going to help us to understand the more advanced problems. So see you in the next video. If you have any questions, just write to me and we will look it over.